Bismillah Rahman Rahim. Uh, Today in our this video, uh, we will discuss how can we use Veristand add-on software, add-on power electronics software uh, for implementing a closed loop boost converter. In our one of the research paper, we have discussed how can we use hardware in the loop and digital control techniques for power electronics teaching. So in this research paper, the case study taken is case study example taken is DC boost converter in a closed loop. All right, but at that time we had power electronics SDK with LabVIEW software, but now we have migrated to Veristand add-on power electronics software. So basically, before watching this example, if you want to go into detail, you may also study this research paper. Uh, Now, in our previous methodology, when we had power electronics SDK with LabVIEW, uh, what we what we performed was that we implemented the closed loop controller for the boost converter using LabVIEW software, and we burnt it into the Stereo, and we designed the boost converter in multisim, or we can also use MATLAB. So in our case, we tried it on MATLAB, but multisim can be also used. Then we loaded this MATLAB circuit of the boost converter into the PXI, and then this digital output signal for this boost converter switch, power switch, was being fed by this Stereo, and this PXI was feeding back the output voltage to this analog input of the stereo. In this way, the loop was closed, and we tried to run a closed loop boost converter. So let me show you. We have a electrical hardware solver. Now also this NI very standard on is also using electrical hardware solver that we have purchased from Opalati. So this facilitates that you can directly load the circuit of the MATLAB into the PXI. And the good thing about this any NI Veristand add-on is that now there is no need of this using the designing the controller in the LabVIEW. You can also make the controller in MATLAB and directly load it into the CP and into the PXI. I mean that the converter and controller both can parallelly be loaded into the PXI system. So in our today's example, these both things can boost converter and its controller will be both running in the PXI, and this stereo will be bypassed. All right. Okay. So this is our boost converter. So let me show you this circuit. We will load this circuit, which is boost converter. All right. And this is a block diagram. Remember previously in power electronics SDK, we as already said this portion controller portion was being designed using LabVIEW and was loaded in MyRio or Crio, and this controller circuit was directly loaded boost converter into the PXI. But now these both things, I mean this controller portion will be also designed in MATLAB. Let me show you. Let me show you the controller. So this is the controller, PI controller for this closed loop boost converter for this circuit. All right, and these both controller and converter both will be running into the PXI, and the Stereo and MyRio will be bypassed. All right, and the mapping these signals, I mean the digital output to the digital output input, this will be mapped inside the Veristand add-on software, and this output will be fed back to analog input inside the inside the software. All right. So previously we designed the this controller LabVIEW controller into the LabVIEW controller into the MyRio or Stereo. This is the LabVIEW software. Now we have the controller in MATLAB, and this controller is a bit improved or have some advanced features as compared to this one. All right. So let's give it a try. So want to create a new project. Maybe I name it boost converter. Go to the configure. Go here to the custom devices, and I want to add my custom device here. You can also refer to my previous videos on NI Veristand add-on before jumping to this video, because I have also explained the steps in my previous videos. Alright. Oh, so let's load the circuit which I shown you here. Alright, so this is a boost converter. Okay. So this may take 1 to 1.5 minutes. So let it be loaded. We are waiting for it. So if you want to uh, go into the detail of this paper, I have already made video on this paper, which you can see on my YouTube channel, which is this one. So you can refer to this video, how can we use Hill setup for power electronics teaching. Yeah, all right. So all right, this is done. Let's refresh it. Right. Uh, let's go to NIMAX. I want to communicate with my this PXI. So to communicate with this PXI, I need to. I have a far left system. Let's copy this IP address and save it. Circuit model is loaded. All right. So you see, I have two switches here. Need to give pulse width modulation to this IGBT switch. So let's select from here PWM. I'm giving built-in PWM. Circuit model PWM0. This is diode uncontrolled, and therefore I'm not giving any. Diode cannot be controlled, so I'm not giving any PWM from the PWM 0 or 1 to the diode. Okay, I left it as it is. So this PWM0, I go to here. This is my PWM0. I make its default duty cycle maybe 50%. All right. This sources, in sources I have one source only. Is U01. Let's make its default value maybe 100 volt. Measurements. So let us say for now I am only interested to see the output voltage, which is my Y04 output voltage of this boost converter. So I am only focusing on my this output voltage right now. All right, so I go to the waveforms. I connect measurements. I want to see this Y04. I make it sampling at 10,000 so that I accurately visualize this Y04 signal on my chart. I save it. Once after these all settings, the next step is to load my this controller, which I already showed you. Okay, so I need to load this DLL file, which is already created. So I go to simulation model, add a simulation model. Pick up this bidirectional boost control DLL file. I load it. Okay. So these are the inputs. You see, these are the inputs, which I can show you here as well. These are the inputs. and these two are the output, duty cycle and V out set point. These are the outputs. All right. Once after this, I need to do mapping. So I go to configure mapping. I need to connect this duty cycle to my PWM0 because in some in one of the case I want this duty cycle to be controlled by this PI controller because to complete the closed loop. Here I connect this duty cycle to this PWM0. Let's connect it. All right. Okay. The next thing is I also need to connect this V out process, which is basically the output of boost converter to Y04. So this I go to power electronic circuit devices. Go here to all right. So I need to connect this measurements Y04 to this my V out process. All right. Okay. I've done these settings. Let's save this. Sorry. Sorry. Let's save it here. Once it is saved, let's close this. See here that this duty cycle from uh, this output duty cycle is being fed to this PWM0, and this Y04 is fed back to this V out process. So this is mapping diagram. After this setting, let's go to add a new screen to visualize the results. I pick up a chart. Let's make it 10 seconds, visible and zero point 0.1, streaming rate 30,000. All right. So one thing more is I also take from here PWM generator to change the switching frequency and to see other results. And one thing more, I can take Q01 from here to change the DC voltage. Maybe in my first case I make it 100. And then one thing more is that I go to the simulation model and I pick up this input here. I make, let us say, my desired voltage to be 150. Ramp rate is 1000. Proportional value of 0.008, 0.005. So you need to calculate these values, tune the PI controller properly. If you don't give these values properly, the controller won't work. So you can use Ziegler-Nichols other tuning methods to find out the correct values of P and I. Or sometimes you can also try hit and try method to get these values. All right. So feed forward duty cycle is 0 in this case. All right. So have a look on this. Uh, you need to give this value of p, proportional, integral. There are three modes of operation. Mode 0 is 0 command where duty cycle becomes 0%. Mode 1 is into manual mode where you can change the duty cycle manually. Mode 2 is where duty cycle is controlled by PI. It means closed loop controller, boost controller. We will use mode 1, mode 2 and mode 0 as well. Alright. So duty cycle, if the duty cycle manual I set it to 50%. Alright. So first I select it to the manual mode, which is basically 1. Then I make the frequency maybe 4500 hertz. All right, and I finally run this model. Let's run it to see y04. This is the output voltage. Remember? All right. It'll take maybe 1 to 1.5 minutes. Target synchronization is complete. So let's make it 100 volt or 150 volt. If I set to mode 1 and if I set duty cycle to 50, you see we are getting 200 volts. So manual mode is working perfect. You see input is 100 volt. If the duty cycle is 50%, so it will boost up to 200 volt. So this is working fine. Let's change this duty cycle to 30%. If I make it 30%, the voltage will decrease from 200 to uh, about almost 140 volt. So the boost converter is properly working. Changing the duty cycle works fine. Right. Now let's jump to the other mode, which is controlling the duty cycle controlled by PI. Alright, so proportional value is 0.008, integral value is 0.005, jump to mode 2, the let's make rand rate 1000. Now you see this is jumping towards 150 volt. My desired is 150, so the output is going towards 150 volt, and accordingly duty cycle is changing. So duty cycle now it is achieved 150 volt. That means my closed loop controller is working fine. I hope you understood how this circuit is basically working. All right, now let's change this just output voltage. If my reference voltage is desired voltage is 200, so duty cycle should jump to 50%. You see this is jumping towards 50%, and the output's going towards 200 volt. Uh, so this is a very state-of-art platform for power electronics teaching and research. Without taking switches in hand, students can implement their controller converters. They can test their power converters significantly in a less amount of time. All right. So let's make it maybe 120 volts. So now the duty cycle should go down. So if it is 220 volt, duty cycle should jump up more than 50%. Right. So I hope you got the idea how this platform is working. All right. So if it is mode 0 means that duty cycle will come in a fault condition where duty cycle will become 0. So mode 0 is also shown over here. So mode 1 is manual mode 2 is control mode. I hope everything is clear. In the next part, we'll make another video. And in our next research paper, we'll discuss how students can use NI Veristand add-on for basically power electronics teaching, where we will bring all the things in detail with some case study examples and how then they can uh, better understand the concepts of control in power electronics. Thank you very much.